Okay, so today we'll concentrate on solid elements. It's kind of a simple element compared to a lot of the others that we've looked at, but we'll see why today. So again, what we have covered so far, the stuff in gray, it was in previous sessions. The solids is today, and this is what's still coming, all the order of elements and so on. Okay. So just again to recap where this fits in, when we look at accurate results, we need all of these accurately. But in this section, we're only looking at discretization. So you still need good geometry, good material properties, and so on. But we're, as I say, concentrating specifically on the meshing and solid element types today specifically. If I just go back to the stuff we spoke about last session, we talked about specific planar type of elements, specifically plane stress, plane strain, the generalized plane strain, and then axisymmetric elements. Briefly to recap, plane stress elements, the stress in the z direction is 0, but there is a strain in the thickness direction. So z in this definition will always be the thickness direction. So this is typical of thin structures loaded in plane. Plane strain is the opposite, where there's no strain in the z direction, otherwise no strain in the normal direction, but there is a stress in that direction. So typically a gravity dam kind of a design. The last one that's related to the previous two is called the generalized plane strain, and that is there is a strain allowed in the z direction, but it's constant for all elements. While if I look at the plane stress, every element can have a different strain in the z direction. So this is actually most accurate for the center sections of really thick structures as opposed to plane strain. So this answer will be somewhere between these two, probably slightly closer to that one than that one. So this is kind of the poor man's Shell's plane strain method. The last one that's not directly related, other than what it looks like, is axisymmetry elements. So that's typically used for something that spins. Not necessarily for stuff that spin, but it's most commonly used for something like shafts. Okay. If I look at solid elements, in terms of setting them up physically, applying properties, it's a lot easier than for shell and beam elements. We only need material properties. The element already has a volume defined simply based on the geometry of that element, where the nodes are and the connectivity to it. Compared to shell elements also need material properties, but we also need to specify a thickness, and that's for the most basic shell element types. We're not looking at composite element types and so on, but there are cases where there may be additional properties that we can specify, special cases like membrane elements and so on. The last one is, if you look at beam elements, visually they're the simplest. Simply a line element connected between two nodes. We again need material properties, but we need a lot more properties. We need cross-sectional areas, the torsional inertia, bending inertia, etc. Then if I want to have stress as an output as well, I need to specify where physically that stress is output, because that nowhere, if I look at the area, torsional inertia and so on, do we have the location for outputting the stress as well. So just in summary, again, the solid elements is the simplest in terms of setting them up. They're not necessarily the best elements in general for a lot of use. Okay, so let's continue on to the shapes that we have for solid elements. Yes, in theory, there's more shapes possible. A few finite element, if any finite element codes will have those. These are the four most common shapes of elements that you'll see for solids. In this case, I'm still looking at first order elements. In a future session, when we look at second order elements, I'll expand this and show the second order element effects and so on as well. Okay, so in sequence, tetrahedron, tet meaning four triangular faces. A pentahedron or a prism element, so we've got a triangular face that we extrude up to the second face. Then something that not all finite element codes have, It's kind of usually used for a transition. We'll discuss why in a little bit. It's a pyramid element, so it's got one square face and then 4 triangular faces as well. So this one has 4 nodes, 6 nodes. This one only has 5. And then finally we have the hex element, which has got 6 faces, which is why it's hex instead of octa or something, but it's got 8 nodes attached to it. If I go back to, I think this was done in the first session, we discussed for membrane element the accuracy of the element. So we looked at a first order tri-element and a first order quad element. And in this case, by going through this, there was just enough information to be able to calculate a constant stress in X, constant stress in Y, and a constant shear over the whole element. Compared to a first order quad element that only has 1 additional node, we had all of those same constant terms, but we could also calculate gradients of stress. So the X stress gradient through the thickness or variation through thickness, and then the Y stress can vary in the X direction. And those question marks were because there's one additional shape that's actually really hard to quantify the stress state for, and that is when that element is warping. So if you lift up the diagonal nodes of that element. And the same way, if we look at solid elements, let's compare the 2 extremes. So again, the element that's defined by only triangular faces and only quadrilateral faces. So if I look at the number of nodes, I've got 4 and 8. So there's now a lot more nodes there than this, as opposed to, if I look at the previous slide again, where it was 3 and 4. If I multiply that node by the number of degrees of freedom for the node, in this case the translation X, Y, and Z, I get 12 degrees of freedom for the element and 24 for this element. I still have to be able to represent 6 rigid body modes, meaning I have to be able to move that element in 6 ways without changing either its shape or its size. If the shape and size does not change, that means there should be no stress. So that leaves me 6 variables to calculate stresses with. And in this case, we've got stresses in X, Y, Z, and 3 shear components. So 3 direct, 3 shear, and that's the only values that we have available to be calculated. So this means the best possible accuracy this element can have is a constant stress over the whole element. In a little bit, we'll see the effect that has in terms of visually what the stress distribution looks at. If I look at the first order X element, I go get to 24, subtract the same 6, but now I've got 18 variables instead of just 6 to calculate additional results with. Okay, so I've increased the number of nodes only from 4 to 8, but I've increased the number of variables by 3 times. So I can still calculate all of the constant values. I can have a stress in the X direction varying in the Y direction. The stress in X can also vary in the Z direction. I'll show these in a little bit. Then we've got stress in the Y that varies in the X direction, stress in Y in the Z direction, and so on. So you'll see that there's only 12 in this case, not 18. But again, we have that same issue with the warping on the faces, which doesn't really produce a useful stress result. So that's the limit. Okay, so if I look at the stress state of this element, it says every one of these faces can have a constant stress in every one of the directions. Said another way, the whole element can only have a single stress in the X, in the Y, and in the Z direction. If I look at this element, try to align your brain so that this is the bottom face and that the top face. On that face, I haven't shown it in the calculations, but on that face, I can again only have a constant stress in this direction, a constant stress in that direction. In other words, if the height is the Z direction, this element has a constant stress in X and Y, but the stress in the Z can vary as a function of the locations. On these faces on the outside, though, I can have a gradient. So the stress in that direction, the X direction stress can vary through the thickness. Same with the Y direction stress, the Y stress can also vary through the thickness. But on the face, if I look at this normal to that face, it's a constant stress in all the directions. This element is slightly worse than this even. it turns out that there's not much advantage in terms of accuracy that we can gain from there to there. So why does this element exist? We'll get to that in the next slide. So just remember this slide. It's usually used just to transition from one element type to another. If I look at this element type, the X element, I can vary the stress in that direction. Let's call that the X direction in the Y direction. But I can also vary the stress in that direction across that face. In other words, I can have low stress and high stress and low stress and high stress for that element. The same goes for every one of the three directions. That means I can perfectly bend this element and get a perfect stress state. This element I cannot bend at all. There's not enough information to be able to bend that element at all. So what about this element? In theory, it lands between the TET element and the X element. In practice, it's not quite that simple. In practice, it depends on the direction you're loading it and the direction that element is aligned at. Okay, so let's talk about compatibility. We'll see what I mean by that last comment, the stress directions and so on in a little bit. Okay, so even if I look at solid elements, not all elements are compatible. By compatible, I mean it makes sense to attach nodes. It's almost always possible to connect nodes together of different element types, but it's not always a good idea. Some of them just doesn't make sense. An example would be connecting an axisymmetry element to a shell element. It's possible, the software may even allow it, but it shouldn't. But it mathematically and physically, there's no meaning to that. Okay, yeah, if you really want to be pedantic, then mathematically you can probably still get an answer out of that. But again, it doesn't make sense. But for solid elements, it's all about the face shape. I cannot connect sensibly triangular faces with quad faces. So in other words, I can connect all of the quad faces from the pyramid, the prism, and the X element. So if I go back a little bit, so these quad faces, all of those, I can connect to any of those faces. That bottom face, I can connect there. This one I cannot connect. Because to do that, I'll have to have, for one of those trifaces, let's say split it along there or along there. The moment I look at the deformed shape, if these diagonal nodes lift up, I get some kind of a curved shape. If I look at triangular faces there, all of those triangular faces trace perfectly flat. There's no possibility for that face to have some kind of a distorted, curved section for a first order element. So that means if I have that kind of a deformed shape, I'll get this really weird gap starting to open up between the elements. I'll get a really, really strange stress distribution there. In practice, it's possible to connect them. It's just the case if it doesn't make sense. Now, the same goes for tri-element faces. All of the tri-element faces are compatible with others. In other words, I can connect all of the tri-faces from a TET, pyramid, or a prism element, but again, I cannot connect a TET element to a X element. No tri-element face can connect to a quad face sensibly. So I haven't tried to break that rule. This is just to show you the effect that the element has on accuracy, those stress distributions that we can represent. If I look at these sections, these beam sections, I've constrained it at the back to perfectly balance the load that I'm applying. So in other words, these sections are in perfect bending. There's a moment there and effectively the same moment at the back. There's no stress concentrations, which means if I look at that bending moment, I expect compressive stress at the bottom and tensile stress at the top, and it has to vary linearly through the thickness. But there and there, since that moment, the way it's applied, it's the same for all of those elements, the same moment to each element. If I look at the meshes from left to right, this was a first order TET mesh, and I've tried to use the same edge length as I'd use on these. So these elements, the X's, I've specified so that the length in that direction is the same as the length in this direction. So in theory, there should be about the same nodes between this and this one. In practice, since the measure has a bit more flexibility to do what it wants toward the inside here and there towards the inside, it may actually have slightly more elements. Okay, the second one is the penta mesh. So the penta mesh, there's 3 of them, and I've created them by taking a tri-mesh on one specific face and then extruding in a specific direction. So in this case, it's triangular face there. So the front and the top in this case has quadrilateral faces, and the 2 sides doesn't have any. If I look at this one, I've meshed the top using tris and then extruded in the thickness. So all of these are in this plane. This one, I've meshed the front with triangles and then extruded in that direction. And if I go back, bear in mind, this stress should be maximum, in other words, tensile at the top and compressive at the bottom. Bear in mind, these elements cannot represent that. It has to have a constant stress, so I'll have some kind of a weird stress state there. So that's to be expected. This one, if I look at this face, that triangular face cannot have a gradient. So on that, there in theory, may be a gradient there, but not in the direction we're actually interested in. But both of these, because the quad face are on the sides, can actually have a gradient through the thickness. The last one is simply the X mesh. And what I've done was, I'll show it in a table a little bit later, I've normalized the displacements all relative to the X mesh, so you can compare what the deformation was. The stresses, I've done a hand calculation and I've normalized relative to that. But for the shear calculation, for the deformation, it's actually slightly more complex. There's some things you have to take into consideration. So what I don't show here is I've just for a reference added a single beam and applied exactly the same load, so you can see what the effect of this would be. Okay, so there's the results for the 5 sections. The dead mesh, this is unaveraged stresses. So as you can see, every element has got a constant stress over the whole element. These are also unaveraged, but it doesn't need to be averaged because the answer actually, every element has the same stress, so it makes sense. It can really well represent that stress state. You'll notice there's a difference in the deformation between the 3. But if I compare these two, actually I expect this answer to be slightly more accurate to this, simply based on there's more elements to represent something in the thickness than there is in this case. So this measure is effectively finer in the direction that matters. This one has got really great accuracy on those faces, but there's no load that actually wants to do anything to those, so it doesn't help. So if I look at the colors, see that blue-green transition? Yeah, so that element is only in, it reports that kind of a level of stress. That one goes slightly higher and lower based on whether the element is closer to the top or the bottom. If I average the stresses, it doesn't get much better in terms of what it looks like for these. For these elements in this specific test case, it's exactly the same. Because again, every element had exactly the same stress state as the one next to it, so there's no reason for the results to differ. Again, if I look at that, I can start vaguely seeing this kind of a pattern, but the result is utterly wrong. Okay, so why do I have both averaged and unaveraged? Unaveraged simply in this case shows the result that the element actually calculated in the background. In general, as long as your mesh is reasonably fine, your average stresses tend to be closer to reality. In some cases, you'll get elements that actually overshoot, or one element, so this is a bad example, but this element and that element, the one may have a very high and the other one very low, and the average is often closer to reality. In this case, these meshes are so coarse that doesn't even happen yet. Good. So if I compare the results, so these 3 are the penta meshes in the same order as this previous slide. So just looking at those, I can see that the stresses all actually looks reasonable, but the deformation of that last one, in other words, the penta mesh number 4, so that's number 3, that one actually has less deformation. So getting back to this, The TET mesh, the normalized displacement relative to the X mesh is only 0.323, meaning I have to multiply that by slightly more than 3 to get to the actual displacement. So that would be an error of, what's it, 200% or something. I have to add double that to that same number to get close to the right answer. The penta mesh, and bear in mind, effect in the direction of interest is actually coarser, is slightly worse. If I look at the normalized stress unaveraged and averaged, it's at least slightly better than the displacement. Interestingly enough, usually in most real models, this will be or converge a bit faster than the displacement. But the TET element, since it can't bend the displacement, is usually pretty bad in any case. If I look at the penta mesh, it's again really bad. And if I look at the normalized stresses, both of those are even lower. So the error for those are significantly greater than the unaveraged stress even. Okay, but now if I look at the penta meshes, what's interesting is that one was horrible, but these are actually pretty decent. If I compare them in terms of displacement up to 3 decimal points, these two are exactly the same. Both for displacement, stresses, unaveraged and averaged. The number 3 was, it over-predicted the stress slightly, both for averaged and unaveraged, kind of as expected, but the displacement was less, and that we could see already in this phase, in this image where it was a bit less visually too already. Interestingly enough, if I use a beam element, I got slightly less displacement, exactly the same stresses though. So which one is most accurate? I'm not certain. I'll have to mesh the X model significantly finer because there's a couple of things that the beam element has taken into consideration, which the solid element does not necessarily take into consideration when it's measured coarsely. But again, that is less than 1% error. It's of the order of 0.1% difference between that penta mesh, the X mesh, and the beam mesh. The point of all this, specifically for the penta at least, is to show you the effect that that direction have on your results. So it's not fair to say a penta mesh accuracy is somewhere between a X and a TET. It's not. It's as accurate as a TET in some directions and as accurate as a X in other directions. So that's why in two directions it's very close, and the other one it's really far off. If I look at the number of nodes and elements, here's a nasty one that popped up. Again, I said the TET mesh may have slightly more nodes because it could refine a bit towards the inside, so that's expected. But the penta meshes and the X mesh had the same number of nodes. In terms of number of elements, the pentas are double, kind of as expected again, because we can simply split each of those X's into two penta elements. But the TET elements was significantly higher in number than the others were. So even if we have a lot more elements, we have a significantly worse answer. Lastly, if I compare the beam model, since this is exactly the intent of a beam type of model, the perfect beam shape, everything, a single element is actually good enough to represent this. So in this case, we had two nodes, one element, and we got to the same answer. And this is one of the things we'll see a lot as we progress towards the later section of the series, is the effect of going from beam to shell to solid in terms of number of nodes, number of elements, and runtime. Good. So just as reference, again, I've said this before, but the displacements is normalized relative to the X model. So I compared the displacement of everything to that one. And for the stresses, these I've done an hand calculation and compared all of those values to that. So in principle, this is what I wanted to discuss in this section is it's the type of element critically determines your accuracy. If I go back to this slide, in other words, this one is horrible in a lot of ways. It's got actually a lot of elements, even if it has a similar number of nodes to a model like this. But even if it has more elements, it's still a lot less accurate. This one, sometimes we'll use if we have a shaft and you want to model, let's say, a cylindrical shaft solid. Towards the inside, I might want to model with these kinds of elements in the center, but you have to be careful in which direction it's loaded. So in that case, if I extrude in thickness direction, I bend the shaft, it's actually in the direction this is good at. So that's okay. So what is the purpose of this element? So that element is purely to transition from this to either these or those, and that one is about as hard to mesh as it is to mesh this one. Okay, last one to note, if I look at the same argument I had about compatibility for shell elements as for solids, there is no issue. A tri-element and a quad-element is compatible because they only connect on the edges. I'm not talking about first and second order elements. They're not compatible. But two second order shells or two first order shells, tri and quad, it doesn't matter, they will be compatible. So just the last one, so I want to make another comment. So in terms of accuracy, this one is horrible, that one is pretty decent. This one is good in the right directions. This one and this one is very similar in terms of accuracy. As I say, it's more to transition from these elements to those. So why do we want to transition? In some cases, we have a structure that's got a complex surface but a really chunky inside. So it's possible to mesh the inside with a lot of X's, which is really efficient, and then use the tets on the outside to form the shape pretty well. So for first order elements, it doesn't make that much of sense. For second order elements, at least, it's a bit better since the second order tet is a lot more accurate than the first order tet will be, as we'll see in a little bit. Okay, then just one last comment. I don't know how many of you have ever heard that statement of you should have at least, and then the number may differ, but it's something like 3 elements through the thickness to get accurate answers. As you can see here, that's not true. The complete answer should be it critically depends on the type of elements, and it also depends on the direction of loading. So if I take this one, for example, and load it sideways in bending, that one will actually give good answers. But in this direction, the loading, it actually gave bad answers. This one, the tet mesh will always give bad answers unless you have a very simple, close to constant stress state. And in addition, for this one, this is where we need to have more than one element through the thickness. The more the merrier. So at about 3, you'll start getting reasonable answers out of this. You'll still get a kind of a weird stress state, but it will start to represent this, even if it doesn't get to those maximum values on the outside. But for these elements, under the perfect case, the kind of a stress state, in other words, kind of load as well, that it can represent a single X element is enough to actually give you pretty accurate answers. Once you get to plasticity, it's more complex because then we have a pretty interesting stress state through the thickness. But for linear elastic stuff, depending on your element type, one element through thickness may be enough or is not even close to okay, depending on which element type we have. Okay, so some of the things that we'll also discuss a bit later on will be distortion of these different element types. Different element types handle things differently. There's one additional comment that I've seen over the years a couple of times, and it has to do with why you'll sometimes want to use either a TET4 or a TRI3 instead of either a X or a quad. And that argument goes something like a TET4 accuracy degrades slower with distortion than a X8, or a TRI3 degrades slower if you distort it than a quad 4. So while both of those comments are true, both of those, TET and the tri element, actually start so much worse than the quad and the X that I don't think you ever reach the point where you get a better answer unless you get to the point where those elements start being so distorted that they become inside out. In other words, you have a quad, but I've got an internal angle instead of external angle. So one of the You take one of the nodes and you move it way across. Imagine that for a quad. If I take that node and I move it there and I get this weird kind of a shape. So that kind of a thing, the element can't solve mathematically anymore. But there's, in those cases, usually ways to fix that in any case. Okay, so that's just a couple of side comments I wanted to make about this. Okay, so just in overview, what we've covered so far was the basics of elements. Yes, we say meshing, but it's not yet meshing. This is just about the element types. So I looked at beam shell, solid elements, planar elements, and some elements that we touched on, but not spent a lot of time on specifically. Okay, then the last one, why do we use the TET sometime instead of vexes? In most cases, it's a lot easier to TET mesh something than to X mesh. There's additional rules. You'll almost always use second order TET because they're so much worse than first orders. So much better than first orders, or at least similar to an X model. In that case, what will happen is it takes a lot less time to mesh, but they solve a lot slower. So it works perfectly for linear elastic stuff. For nonlinear stuff where you need lots and lots of iterations, we'll tend to rather go for the first order X elements, which is more efficient than second order TETs in terms of runtime. Okay, so that concludes today's session then on elements and meshing, solid elements specifically. Thank you for your time.
Hi, it's Gary here. I know that they are quite small, basic examples. Is there any chance you could share those models, Gerrit, if that's possible?
Yeah, it's not an issue. I can send it to you easily.
Or you could just send a description of them. I'd like to show some of the guys that haven't seen this type of, the different types of meshes in the office here. It would be good for the guys to see.
Yeah, sure, it's not an issue. Just send me a mail.
No problem.
Cool.
100%. Thank you.